Okay, our last lesson for chapter 6 rather. 6-9 formulas for cosine 2x and sine 2x. So as of right now, we've studied the Pythagorean identity, and we've looked at the identities for cosine of alpha plus beta and cosine of alpha minus beta. We've also studied the sine of alpha plus beta and the sine of alpha minus beta. Now we're going to use these identities to develop the cosine of 2x and the sine of 2x. These are referred to as our double angle formulas. So double angle, 2 times the angle measure. So in our identity, alpha and beta would both be equal to x. Using the expansion, cosine of the first times cosine of the second, change the operation, sine of the first, sine of the second. Cosine times cosine would give us cosine squared. Sine times sine would give us sine squared. So this is our first double angle formula for cosine. Now on the right hand side, you'll see there's a proof for each of the double angle formulas using an angle measure. So you can look through that as well. Now, because of our Pythagorean identity, the fact that cosine squared plus sine squared equals 1, we can use the identity to derive 2 more double angle formulas. So first one, if I think about solving the Pythagorean identity for cosine squared, I would subtract sine squared from both sides. So in the identity we just saw, the double angle formula, I'm going to replace cosine squared with 1 minus sine squared. No need, on the next step, we don't need the parentheses, all right, nothing to distribute. So I have 1 minus sine squared minus sine squared. Combining like terms, we get our second identity for a double angle formula for cosine. And then lastly, going back to the original identity, cosine squared x minus sine squared x, and manipulating the Pythagorean theorem for sine squared. All right, so we're going to solve this by subtracting cosine squared x from both sides into the first identity for the double angle formula. So in the first identity we derive, we're going to replace sine squared with its equivalent 1 minus cosine squared. Now because of the order of the identity, we have to distribute the negative. So cosine squared x minus 1 plus cosine squared. Combining the like terms of cosine squared, we get our third double angle formula. So when you're asked to find the cosine of a double angle, you have one of 3 possibilities you can use. Now, you can study one and know it really, really well. So you can know one really well, or just be able to derive all 3 of them based on the original double angle and what the Pythagorean identity does for us. Okay, so example 1 goes through a step-by-step example of how to use the double angle formula. Okay, so you are expected to read through that, please. Example 2. Let sine x equal 12 over 13. Find the cosine of 2x. Now remember, you guys will have a formula sheet on your homework quiz and on your test. So look at the given information. The given information I have is the value for the sine function. So I'm not going to use either identity. That involve the cosine function. It wouldn't make sense for the information that's given to me. So let's use the 1 minus 2 sine squared x. Okay, it makes the most sense. We don't have to solve for any other type of information. It's right there in front of us. So cosine of 2x is 1 minus 2. Now remember, when the exponent is between the trig function and the variable, the entire function is squared. So when I make my replacement, I'm not solving for x, I'm replacing all of sine x with 12 over 13. So the entire thing gets substituted in for. Don't put 12 over 13 in for x. That's not the given information. So square the top, square the bottom, top times top. All right, if you imagine putting 2 over 1, bottom times bottom. Now in order to subtract fractions, we know we need a common denominator. Common denominator would be 169. So multiplying the first fraction by 169 over 169. And this gives us negative 119 over 169. So that would be our final answer. Now on some examples, we'll give you a piece of information and tell you which identity to use. So if I tell you to use cosine squared minus sine squared, well, you have the cosine element, but you need the sine value. In order to do that, we would set up a right triangle and use our Pythagorean theorem. So example 3, again, it's a step-by-step worked out solution. So please read that over and be able to use it in the homework problems. All right, double angle for sine. Using our expansion for sine of alpha plus beta. All right, alpha and beta are the same thing. Sine of the first times cosine of the second. Keep the operation the same. Cosine of the first, sine of the second. Remember that the order in which we multiply does not matter. So if I keep my first term the same and I just change the product to sine times cosine, notice we have the exact same terms. So combining like terms, we have our one identity for the double angle of sine. Okay, one identity for sine 2x, 3 identities for cosine of 2x. But the thing with the double angle for sine, it requires that you have the sine and cosine value for every problem. All right, so the example of using the Pythagorean identity and setting up a right triangle, we'll use that here. Sine of 2x, 2 sine x, cosine x. Okay, I know what my sine value is. Now we just need to determine what the cosine value is. All right, so following the steps that are outlined in example 3, first thing we do, set up a right triangle. Now, I draw my triangle specific to the quadrant. Look at the information that's given here for x. X is between pi over 2 and pi. So I'm going to draw a right triangle in the fourth quadrant, or excuse me, the second quadrant. I always put my angle measure with the horizontal. Okay, if you remain consistent, then I think it'll just help you solving when x is given in any quadrant. Look at my given information. Sine is 3/5. The sine of x, opposite side over hypotenuse. In order to determine what the cosine of x is, we know cosine is adjacent side over hypotenuse. So I have my hypotenuse. Now how would I find my adjacent side? That's where my Pythagorean theorem comes in. A squared plus b squared equals c squared. I'll call it a for adjacent. All right, so 25 minus 9, a squared equals 16. When we take the square root, we have 2 answers that exist. All right, side lengths cannot be negative, so I'll write that my adjacent side is positive 4. But now we have to incorporate everything we know about trig. If my angle measure is in the second quadrant, I know that only the sine function has a positive value. So the side length that represents the adjacent side to the angle is 4, but because the cosine is in the second quadrant, it has to have a negative value. So I replace negative 4/5 with the cosine of x, multiply across, 2 times 3 is 6, times negative 4 would give me negative 24 over 25. Now the good thing about the sine identity, you don't have to ever get a common denominator because we're strictly multiplying. It does, however, require that you would use the right triangle because we'll more often than not just give you one piece of information. All right, evaluate the sine of 2x given the cosine function. So 2 sine x times cosine x, that's our identity. So sine of 2x would be 2. We need the value for the sine function. Cosine is already given as a fourth. And we're told x, our angle measure, is between 3 pi over 2 and 2 pi. So it's in the fourth quadrant, verifying that the cosine value is positive. Draw a right triangle in the fourth quadrant. Put your angle measure with the horizontal. Fill in the given information. Adjacent side, 1. Hypotenuse is 4. So I need to find my opposite side. I'm going to use the Pythagorean theorem. 1 squared plus opposite side squared equals hypotenuse squared. That looks too much like a 0. We'll just keep that as b. So I have b squared. 4 squared is 16. 16 minus 1 gives me 15. So b would be the square root of 15. So square root of 15 is my opposite side. In the fourth quadrant, only the cosine function is positive. So when I go to fill in my sine value, sine of x is opposite over hypotenuse, I have to make sure that the ratio is negative. So negative square root of 15 over 4. Multiplying 2 times 1 is 2. Make that a negative 2 times the square root of 15 all over 16. Nothing needs to be rationalized. The square root is in the numerator. So that would be our final answer. Okay, so now, given the sine value, evaluate cosine of 2x. Since it's cosine of 2x, we have our 3 identities. I'm going to use my identity that is strictly in terms of sine. So 1 minus 2 sine squared x. 1 minus 2, the sine is given as negative 8/10. I'm going to square that. 1 minus 2, negative 8 squared, 64 over 100. I'm going to do a little bit of simplifying. So 1 minus 64 over 50. Just to help you with the common denominator, divide both of these by 2, 32 over 25. Now when I go for my common denominator, it's a little bit easier. All right, multiply the 1 by 25 over 25, minus 32 over 25, and my final answer would be negative 7/25. Sine of 2x, 2 sine x times cosine of x. We're told the sine is negative 8/10. Now we need to determine the cosine. So we have to look at the quadrant between pi and 3 pi over 2. So that's third quadrant. Oopsie, sorry. Create a right triangle in the third quadrant. Put x with the horizontal. My sine opposite side over hypotenuse. Now I can disregard the negative because side lengths can't be negative. My sine value has to be negative because of the angle's placement in the third quadrant. So adjacent side, a squared plus b squared equals c squared. 100 minus 64 would give me 36. So this side length would be 6. Cosine in the third quadrant is negative, adjacent over hypotenuse. Now we can do all sorts of simplifying here. This would reduce to negative 4/5. Negative 6/10 would reduce to negative 3/5. And then we won't have to reduce the product. All right, positive 12 times 2 would give me 24 over 25. All right, last example. Suppose that sine of alpha is given and sine of beta is given, where alpha is in the second quadrant and beta is in the third quadrant. Find the sine of alpha minus beta. So not a double angle. Sine of the first, cosine of the second. Keep the operation the same. Cosine of the first, sine of the second angle measure. When I look at this, I only have the sine values for alpha and beta. So I'm going to plug that information in. I'm going to run out of time here. So finish this problem.